Hi everybody, I hope this video finds you well. In today's video, we're going to be finishing up section 1.5 from your textbook, which was your introduction into modeling using differential equations. In the first video for section 1.5, we spent a lot of time sort of going through and developing sort of explicit formulas for some of the famous differential equation models. And we saw how to do that for exponential growth, we did it for logistic growth, we saw how to handle sort of Newton's law of cooling. We went through and basically worked our way and re-derived famous results using differential equations. In this video, we're going to do something a little bit different, and we're going to instead focus on very specific situations, building differential equations that model them based on information about the proportionality, and then instead of trying to explicitly solve those differential equations, we're just going to be interested in analyzing their sort of equilibriums and long-term behaviors. And this, of course, is going to be sort of nice because it means we're not going to have to go through any of those sort of messy derivations with lots of sort of nasty integration or anything like that. We're just going to see how much information we can sort of glean from understanding the equilibriums, understanding the differential equation, and analyzing those behaviors. So let's go ahead and take a look at our first example here. So suppose we're studying the population of a fish, of a particular type of fish in a small lake. So we know this population of fish, if left alone, will grow according to a logistic growth model, i.e. it grows directly proportional to the product of their current population, measured in thousands, and the difference between their current population and the carrying capacity of the lake, which apparently is 10,000 fish. We know that the constant of proportionality for this growth is 1/20th, when the population is measured in thousands and the time is measured in months. So notice that that's sort of telling us the units we're going to be using here, the population in thousands, the time in months. Further suppose that 800, in other words 0.8 thousand fish, are harvested from the lake each month. So we have this population of fish that are sort of growing naturally according to a logistic growth model, but then they're also being harvested at a sort of constant rate here. So what we're going to do is we're going to try to write down a differential equation that models the population with P being measured in thousands and T being measured in months. Then we're going to analyze the equilibriums, and then we're going to talk about some long-term behaviors depending on if the current population is 7,000 fish, so if the lake sort of starts with around 7,000 fish, and then what happens if the current population is 1.5 thousand fish. So let's go ahead and start by trying to build a differential equation for this. So for part A, we want to go dp dt, the change in the population with respect to time, and we'll just try to read through this and translate all this information into some mathematical statements. So we know that they follow this logistic growth model, so they're directly proportional to the product of their current population and the difference between their current population and the carrying capacity. We know that the constant proportionality is 1/20, so we can put 1/20 times their current population, which is going to be P, whatever variable we're sort of using, which in this case is P, and then times the difference between the population and the carrying capacity. We know that when using carrying capacity, it should go first, so we should have 10 minus P there. And of course, notice we're doing 10, not 10,000, because we're measuring everything in thousands. Notice that this 10 minus P makes sense. If P is somehow over 10, if we're above the carrying capacity, then this will be negative, causing our population to decline. If P is if P is less than 10, then we're below the carrying capacity. This will be positive, causing the population to grow. So this handles the sort of logistic growth part of it, but now we also need to take into account that there a 0.8 thousand or 800 fish are harvested from the lake each month. So let's think about that as a sort of separate component here. Keep in mind that we're modeling the differential equation. So if there wasn't this growth and we were just saying that we were losing 800 fish per month, then, well, we would just have our minus 0.8. And notice that should make sense because, again, if we didn't have this, then we just say dp dt, the change in the population per month, is minus 0.8 thousand. But we have this growth aspect, and then we have this harvesting aspect. And of course, the harvesting is constant because it's always 800 fish per month. Okay, so there's our differential equation. Let's go ahead and see if we can determine all the equilibriums for this population. How would we determine those equilibria? Well, they'd have to be constant values for the population. In other words, they'd have to be constant solutions to this differential equation. So let's go ahead and see if we can do that. So equilibrium, this would be P equals a constant. We could use any letter here, C or K. I think in the past we've been using K, even though we sometimes use that for constant proportionality, but I think it's safe as long as we just sort of note equilibrium are going to be P equals a constant. So if P is a constant, then dp dt is going to be equal to 0. Remember, that also sort of is why we call it an equilibrium. It's an equilibrium because the rate of change at that would be equal to 0. In other words, you wouldn't change at all. In other words, you'd be at an equilibrium. Over here, we can plug in the k. So we have 1 over 20 times k times 10 minus k minus 0.8. So we just need to go ahead and solve that. We can bring the 0.8 over. So 0.8 equals 1 over 20 times k times 10 minus k. Then I suppose we can solve by multiplying 20 on both sides. So it looks like we get 16 is 10k minus k squared if we multiply out. And then we can bring this stuff to the other side. K squared minus 10k plus 16 is equal to 0. And then it looks like we should get k minus 8 and k minus 2 equals 0. So we get k equals 8, k equals 2. So it looks like we've figured out 2 equilibrium. It would be P equals 8, P equals 2. So that would be 8,000 fish and 2,000 fish. Now, this is sort of interesting here, and this is actually why we're working through this with some numeric values. You'll notice that the equilibrium here are maybe not what you would traditionally expect for the logistic growth model. If we didn't have that harvesting component, the equilibria, very obviously, would be P equals 0 and P equals 10,000. Right? You would be where you have no population or you're immediately at the carrying capacity. But that's not the case here. Imagine that P equals 10. If you're right at the carrying capacity of the lake, then the population isn't going to grow at all. But you're still going to be harvesting, meaning that the population will decline and it won't be at an equilibrium. Same thing at P equals 0. It doesn't quite make a lot of sense, but if there's no fish in here, then actually your population is going to be declining, again, not realistically, but mathematically it'd be declining into the negative values, so of course that doesn't make sense as an equilibrium. So we're basically saying that the equilibria have shifted sort of towards the center. You can have an equilibrium at the higher end of 8,000, where you're not quite at the carrying capacity, so the population is still growing, but it is balanced out by the harvesting, or a population of 2,000, where the population is very low, so it's growing pretty rapidly because of the carrying capacity, but again, it's balanced out by the fact that we have that harvesting. So 2 equilibria here, 8,000 and 2,000, or P equals 8 and P equals 2. All right, so now, before we get into this analysis about what happens at 7,000 and 1.5, let's do a little bit further analysis with these equilibrium. We can actually think about if these are moments where the rate of change is 0, we can sort of almost do like what you did in 190 when you were curve sketching and think about what the derivative will be on the other sides of these. So let's make a little sort of number line here. Obviously, the low end is going to be sort of like P equals 0. That's sort of just a bound because it doesn't make sense to have a population go below 0 in terms of a physical population. And then there's P equals 2, which we know is one of our equilibrium. And then down here, we'll say that that's P equals 8. That's another equilibrium. So let's think about what happens to our population in each segment here. How can we do that? Well, we can sort of think about choosing a typical value in here and plugging it in. So let's say we take as a test something like P equals 1, which would be over here. If we take P equals 1 and we plug it in here, looks like we'd get like 1 and then times 9. So it'd be 9 over 20. 9 over 20 is like 0.45 minus 0.8. That's going to be negative. We're going to get a sort of negative slope. So in other words, in this entire section, the population is going to be decreasing. So if we have less than 2,000, the population is going to decrease. In other words, the population is not going to grow swiftly enough to make up for the harvesting that's going on, and the population is going to decline. If we choose something in this range, between 2 and 8, I don't know, let's just do a test value of like P equals 5. If we plug P equals 5 in there, we get like 5 times 5. That's 25. 25 divided by 20 is definitely bigger than 0.8 because it's bigger than 1. So that's going to be positive, and that means that the population is going to grow. So no matter where you are between sort of 2 and 8,000, the population is going to rise to that equilibrium of 8,000. Finally, if you're above that 8,000, we can probably guess what's going to happen, but let's just do a test value. Let's say like p equals 10, for example. On this side, if you do p equals 10, this is going to be 0, and you're going to decline. Where are you going to decline towards? Well, you're going to decline back towards that p equals 8. And you know what? Just because visually it's sort of bothering me, let's draw that arrow sort of declining that way, because the population is going to shift towards here. So what do we notice here? Well, what we're basically saying is if your population starts in here, it's going to decline down to 0. In other words, the population is going to run out. If your population starts somewhere between 2,000 and 8,000, it's going to rise until it eventually tends towards 8,000. And if your population starts above 8,000, it's going to tend down back to 8,000. If for some reason you started right at 2,000 or 8,000, then it would just stay stable at those equilibria. It's a little beyond the scope of our class, but there's a little bit of terminology in like this sort of equilibrium analysis, which is what we're sort of doing a very basic example of here, where we would call this 2,000 equilibria unstable, because notice that if we have a slightly larger population, 2010 to 2020, something like that, well, the population would rise. But if we had a slightly less than 2,000, like 1900, it would decline. So in other words, right here at this equilibrium, things are very sensitive. If you're a little bit above 2,000, you'll increase. If you're a little bit below 2,000, the population will decrease. This is sometimes referenced as an unstable equilibrium. This equilibrium, though, is called stable, because even if you're a little below 8,000, you'll tend up to 8,000. And if you're a little above 8,000, you'll tend down to 8,000. So it's not sensitive to the initial condition. So this is what's sometimes referenced as a stable equilibrium. Again, that's not stuff that we're going in depth in, because we're eventually going to be moving into just solving differential equations, not trying to do this sort of outside equilibria analysis. But just in case you guys ever take courses in that, wanted you to sort of hear some of those terms. All right, now that we have this nice little equilibrium analysis, doing parts C and D should be very easy. So if we think about part C, so our initial population, P at 0 is 7,000. That means we're right in here. That means the population is going to increase, and tend towards that. So the long-term behavior will tend towards that 8,000 fish. So if we start with 7,000 fish, they'll be growing, they'll grow slowly, it'll be mostly balanced out by that 800 that are being harvested on a regular basis, and in the long run, you'll tend towards 8,000 fish. What about the 1.5 thousand? Well, for that, if we have our initial population here, P of 0 equals 1.5, well, then we'd be over here. And unfortunately, the population would not grow rapidly enough to make up for what was being harvested. So the long term here in real life would mean that we would go to 0. Now, of course, mathematically, the long term would be we would shoot past 0 and go into negative fish, whatever that means. But of course, if we were really thinking about this as a biological model, the long term would be that the fish population would go extinct. So this is an example of doing what is sometimes called equilibrium analysis. Notice that it completely avoids needing to solve the differential equation, and that's actually a good thing here, because this differential equation, while pretty simple, is actually not a separable differential equation. You can't separate this thing because while you have these components of p, you have this second term that doesn't involve p, so you can't factor the dependent variable out. So unfortunately, with what we've learned so far, we wouldn't be able to solve this. So it's very nice to get this amount of information based just on the differential equation itself. Let's try this one more time, sort of doing this equilibrium analysis with another sort of situation, also introducing something sort of similar to carrying capacity, which we encountered here, called the threshold population. So we're going to suppose that we're studying a population of a herd of deer in a large area. So we know, again, that population of deer, if left alone, will grow directly proportional to the product of their current population and the difference between their current population and their threshold population, which is 30. Now, threshold population is a term that's used a lot in biology. Basically, threshold population is sort of the opposite of carrying capacity. Carrying capacity is the maximum population that an area can sustain. Threshold population is the minimum population necessary for whatever you're studying to continue surviving and moving forward. So a threshold population sort of is the minimum size, and we're saying in this case it's 30. Now you'll notice that in this case we're assuming there's no carrying capacity because we're basically saying our herd is in such a large area, there's no sort of issue with resources there. We know that the constant of proportionality for the growth is 1 over 900 when the time is measured in months again. And then we're going to further suppose that predators eat an amount of deer directly proportional to the current population with a constant of proportionality of 1 over 20. This little part here, you can basically say that predators are eating 1 out of every 20 members of the herd every month. So in other words, the more deer there are in the herd, the more that are going to be eaten by these predators. Okay, so let's go ahead and write down a differential equation that models this. So once again, we'll start by just saying dp dt, and we'll try to write down all our information. Well, we know the first constant of proportionality we have is 1 over 900, and then we're supposed to do the product of their current population, which is going to be p, with their the difference between their current population and threshold. Now, normally if it was carrying capacity, we would do c minus p, but for this case, we should probably do p minus 30. The reason is here, if p was somehow below 30, then this would be negative and our population would decline because we're below the threshold population. But if p is greater than 30, then we're above the threshold population. This will be positive and our population will increase. So there we go. If they were left alone, this would be our differential equation. But we know that predators eat an amount of deer directly proportional to their current population. So we would have minus, because this is obviously going to be reducing their population, 1 over 20 times p. And of course we're using p there because it's directly proportional to their current population. So there we go. There's our differential equation for modeling this population. Again, we're going to try to do the same thing where we come up with all of the equilibria here. So for B, we're going to do our equilibrium, which is P equals K. So, of course, equilibrium means that the population would be stable there. So this left-hand side is going to be 0 because the derivative of a constant is always 0. Then we have 1 over 900, K times K minus 30, minus 1 over 20 times K. All right, a little bit messy, but I guess we can go ahead and multiply, I guess, both sides by like 1800 to just clear all the fractions. Yeah, 1800 should work. So then we'd get 2k, k minus 30, and 1800 here would be minus 90k, I guess. Yeah, that looks okay, I guess. Did I do that correctly? Yeah, I think so. All right. Well, we'll find out. If I mess up, we'll go back and fix it. All right. We can factor a k out of that. So we can get k, and then we can distribute that 2 in. So we get 2k minus 60 minus 90. Yep. Okay. And then we get k and 2k minus 150. And then looks like we should get that as... we can factor a 2 out again, 2k and k minus 75. So it looks like our equilibrium would be k equals 0 and k equals 75. So we have 2 equilibrium populations, p equals 0 and p equals 75. So if we have 0 deer, according to this model, we'll have a stable population. That should make sense. 0 deer means that the population won't be increasing because there's 0 deer to increase from, and nobody will be eating them because there aren't any. So p equals 0 is definitely going to be an equilibrium. P equals 75 is basically saying that the growth in the herd, based on that sort of model here, especially since we're over the threshold, there'll be positive growth in the herd, but it'll be completely balanced by the amount of deer that are eaten by predators. So there'll be a perfect balance between the new members and what are then also consumed by the predators. So we've got 2 equilibrium populations there. Let's study the equilibrium behavior, just like we did in the other. So let's draw our little diagram. We have 0. We don't need to think about anything lower than 0, and we have 75. We know that these are both our equilibrium. Let's choose some test values in here. We can choose anything because, again, it's always going to act the same because these are the moments where the derivative became 0, so it can't change signs anywhere else. To make things easier, just to do in our heads, I'm going to choose p equals 30 here. The reason p equals 30 is so easy is because that's the threshold, so that's going to just be 0, and that's going to mean we're definitely going to get negative. So that means we would get a negative slope, which means the population would decline. So if we are below that 75 population, then our population is going to decline down eventually to 0. If we have a population above, I don't know, maybe we'll pick 90 or something to make it a little bit easier. Well, 90, if we put in 90 here, looks like we get 90 over 900, which is 1/10 times 90 minus 30. That's 60, so it sounds like that's 6. And then here we'd get 90 over 20, which is 4.5. 6 minus 4.5, that is going to be positive, so the population would increase. So if we have a herd that starts above size 75, then it's going to increase. And since we don't have a carrying capacity, it is going to increase without bound. In other words, the growth will be so great that even though more and more will be consumed by the predators, their population is just going to keep growing forever onwards. So there we go. There's our equilibrium, right? If we're at one of these points, it won't move at all. And here's what happens in either sort of side of it. All right, let's go ahead and then talk about these. For C, if the current deer population is 40, well, it would definitely be above the threshold, so there would be growth in the population. But unfortunately, what would be eaten by predators would outweigh that growth, and what we would see is we would see a decrease because we'd be over here. P equals 40 would be somewhere in there. So the population, so P of 0 equals 40 would lead to population 0 in the long term. So it would come out as population 0 in the long term. Eventually that population would go extinct because even though initially there would be some growth in their population, the predators would outweigh that. Eventually it would dip below the threshold, and then the population would decline very rapidly because not only would the herd not be sort of growing, but they would still have predators consuming them. All right, so for D, let's go ahead and take a look at that. That says if the current population is 90, well, we'd be somewhere over here. We actually tested that. What would be the long-term behavior? Well, they would actually grow uncontrollably according to our model. So would lead to population, well, positive infinity in the long term. Because we didn't put any sort of carrying capacity, there's nothing to stop the growth. Even though the predators will eat more of this population in the long term, well, the growth will be outweighing that, so the population will continue to grow. Okay, so for these two examples, what you guys should really take away from this is how to read through an explanation of a model or relationship and phrase it as a differential equation, and then how to analyze the equilibrium. I want to do one more example. We're not going to do the full equilibrium analysis because the actual next example doesn't have nice equilibria. I just want to focus on writing down the differential equation in the next example. But the next example is slightly more complex because it has what we will see is sort of a changing carrying capacity. So let's look at that example as our final one for building models with differential equations. So for this one, we're going to study that you're looking at a social media platform that is informing their users about changes to their privacy policy. So they're trying to let the people who use their social media platform that there's been changes to this privacy policy. So what we want to do is we want to model the number of users P who are aware of this new privacy policy. So we're basically modeling the people who use this website and who are aware that there's been these changes. So we're told initially that the social media platform has 10,000 or 100,000 users. That's not what we're modeling, though. And 20,000 are aware of the new privacy policy. So that part right there is actually what we're interested in because we're trying to model the ones who know about the privacy policy. The number of users who are aware of this new policy grows proportionally, this is the part telling us about the differential equation, to the product of the number of users who know about this policy and the number of users who do not know about the policy. Okay, so we'll have to use that. Finally, we're going to suppose that the platform is gaining new users as a constant rate of 2,500 per month. So in other words, the amount of people who just use this platform is always increasing. We're going to make the assumption that any new users are not initially aware of the privacy policy. So anybody who jumps on and starts using this does not know about the new privacy policy. So we're going to try to write out an IVP to model this using only the variable P for the number of users who are aware of the new privacy policy, and T for the time in months. Of course, we'll also need a constant of proportionality, but that's not a variable, that's just a constant. So let's see if we can go ahead and do this. We need to write dp dt, come up with a model for that, and we'll also need our initial condition, P of 0. Okay, so let's start by actually seeing if we can figure out that initial condition. What is P representing? Is it the number of users? If so, it would be 100,000. But it's not. P is supposed to know the number of users who are aware of this new policy. So P of 0 here would be that 20,000. We know that initially 20,000 people are aware of what's going on. All right, now let's look at the proportionality piece. It says that the number of users who are aware grows proportionally. So we've got our K, because it's directly proportional, to the product, so we're going to have to multiply two things. The number of users who know about this policy, well, the people who know about this policy, that's what we're trying to model, so that would be P, times the number of users who do not know about this policy. Well, for now, let's call that N. Now, of course, we can't really get away with this because this would be multivariate. We need to try to phrase this N in terms of stuff that we know. Well, what can we say about N? Well, N is equal to the people who do not know about this policy. Well, that should be the difference between how many users we have and the people who know. So that should be the number of users minus P. Well, it almost seems like this is just straight carrying capacity. We could just say, well, let's take the 10,000, pop it in there, and say 10,000 or 100,000. I don't know why I keep saying 10,000. I apologize. 100,000, pop that in there, and say that N equals 100,000 minus P. Unfortunately, though, that does not take into account that the number of users is growing at a constant rate of 2,500 per month. So what we have to recognize here is that the number of users is actually based on that variable T, the time in months. The number of users is 100,000 plus that 2,500 T. In other words, the number of users at T equals 0 would be 100,000. Then it would be 102,500, then it would be 105,000, so on and so forth. So there's our formula for the number of users. That tells us that the people who are not aware is actually 100,000 plus 2,500 T minus P. So there we go. Now we can actually phrase this in terms of T and P, the variables we want. Throw that in there, and then we have dp dt equals K times P times 100,000, said it correctly for once, plus 2,500 T minus P, with the initial condition that P of 0 is 20,000. All right, so that right there, this is probably the sort of most complicated one we've seen. What I want you guys to sort of understand here is that what's going on with this example is that this is almost a logistic growth model, because we're sort of measuring the population and the difference between the population and the carrying capacity, which is 100,000 at least initially, because you can't have more people know about the policy than who use the network. But the big difference is that the carrying capacity is changing. Over time, there's more and more users, so we actually have an equation, not just a constant, but an equation for the number of users, and that goes in as our carrying capacity there. Otherwise, this is pretty much a standard logistic growth model. You'll notice that, well, we're not going to talk about equilibrium, not because, well, we didn't ask that question, but the reason is that this isn't going to really have easily findable equilibrium because it depends not just on the number of people who know about this, but also about this time. The fact that there's an instance of the independent variable here basically throws out the potential for equilibrium, for just constant valued solutions to this. If you want, you can actually sort of try to analyze it. The only constant valued solution you would find is just if P was originally equal to 0, because then if you had P equal to 0, then this part would be 0. But you won't find any other equilibria that are of that constant form because of the fact that there is actually the independent variable in the expression here. All right, so that's a lot of stuff about different types of differential models. This wraps up section 1.5 for us. In our next video, we'll be moving into 1.6, changing gears back to actually looking at another way of solving differential equations. And that's sort of going to be our rhythm here at the beginning. We'll sort of learn a little bit more about solving some differential equations, then talk a little bit more about some models, and then get back to some more techniques for solving differential equations. So our next video will take us into our next technique called linear first-order differential equations for section 1.6.